Welcome everybody to our today's installment on the lecture on image processing, retrieval and analysis, and it has already happened. Right? I told you that the number of attendees will decrease. We're not down to 1/3 yet, but we're getting there. Don't worry. Everything is being recorded. You can watch it at home. Let's see what we are going to do today. At first, we will ever so briefly remind ourselves as to what has been discussed last time. And then we'll start with, let's say, the first really important chunk of content of this lecture, namely the question as to how we can think about digital images in the sense that we want to do something with digital images. So how would we have to think of them so that we can do something with those images? In particular, we'll look into the idea of understanding images as sets, understanding images as arrays, something we did last time already, and then understanding images as functions. Now, once we have familiarized ourselves with these ideas, we can then begin to look into the topic of doing something with images. For instance, today's lecture will look into how to derive images. And once we have seen that, we can actually have a look at the first artistic image effect, the emboss effect. Close with a summary and a brief discussion as to things you might want to think about at home. All right, here we go. Last time we basically spent the entire lecture on discussing how photographs are being recorded. Right? There's different ways of creating digital images. One way is to, use programs such as Photoshop and create them from scratch. But in a certain sense, we are more interested in images that have been recorded as pictures from our daily environment, in particular pictures that have been recorded using digital cameras, and we looked into how digital cameras work. And the main component, in a certain sense, the main component of such a digital camera is the CCD chip, charged coupled device, a semiconductor device that consists of a lot, and this is just 12, but it's much more in practice, tiny photosensitive elements that are able to turn light waves or photon counts into charges, so basically electron counts, which we can process. We looked into how color images are recorded. We saw that there's basically two ways of doing this as of today. Other ways might be invented, you never know. One way of recording color images is to record 3 different images at the same time, where one of the images would somehow represent the red content of the scene that is being recorded. The other would represent the green content of the scene that is being recorded. And the third one would represent the blue content of the scene. And why this is done in terms of red, green and blue will be discussed in much more detail much later on towards the end of this semester. But color images can be thought of as a superposition of a red, a green and a blue image. And the question is how to get these images, and one way of doing that is to put a prism behind the lens. So this is supposed to be the lens of the camera. Light, shutter opens, light is incident to the lens, it's being focused on that prism, and that prism splits those beams of lights into 3 components, and they are being sort of deviated, and so we can record the red, green and blue part of the scene. This is great. This gives very high quality color images, but it is rather expensive. It requires to have 3 CCD arrays, and it requires to have these prisms. So this is technology that is well, not that expensive anymore, but still much more expensive than a simpler idea where we basically just have one CCD chip, but there is a filter superimposed over this image. These are lots of tiny shares of glass, yeah, according to the coloring here, you can imagine that this tiny chart of glass will only sort of will filter out anything that is not in the blue part of the electromagnetic spectrum. These kind of charts will filter out anything that is not in the green part, and in that sense, the image that is being recorded is well, again, contains blue, green, and red contents, but somehow something like that is created. This is, of course, not really desirable. It's much cheaper than the idea of splitting beams of lights into 3 components. Since there are so many, and actually we're really talking about millions of these things on a CCD chip, it does not really make a difference to the human eye. We just have a certain spatial resolution in our visual system. So with dirty tricks like that, we can indeed record color images that look convincingly to the human visual system. And a very, very crucial point we discussed last time, which I have to re-emphasize today, is the fact that digital images are digitized and quantized. And by digitized, I mean that the domain, that is the spatial aspect of the image, the X and Y components of the image, is discrete. It's not something continuous, but as it is being recorded by devices like that, which consist of lots of discrete, tiny units like that, but they are discrete, digital images are digitized, and they are quantized, and by quantized we refer to the fact that even though the intensity that can be recorded by one such element in these CCD chips can, to all intents and purposes for the human visual system, vary continuously, it is not recorded in a continuous manner. But it is quantized in the sense that, let's say in this example, we would record intensity values between 1 and 15, but everything that would be recorded is actually just 5 intensity values. And we see that the first 3 intensity levels that this chip can actually record are being sort of merged into just 1 intensity level. And this is indeed what is done in digital cameras. What digital cameras typically, and I have to be careful here because technology advances, but up to now, typically what they record is 1 byte of, let's say, intensity information per CCD element. And of course, 1 byte consists of 8-bit, and with 8-bit we can represent 256 different intensity levels. And from now on, I may use the terms intensity levels and gray value levels synonymously, so don't be alarmed. And because, once again, the domain is quantized and the range is quantized, digital images are digitized and quantized. Okay, now, this is all good and well. Now we know how they are recorded and how they look like in memory. They are being stored in terms of arrays, sometimes in terms of 3 arrays representing 3 different color channels, but they're recorded as arrays in the digital memory. This is good. How do we work with these arrays? Well, one very simple idea as to how to think in a more abstract manner about digital images is to consider them as pixel sets. And by that, I would refer to an image, I, as a set of pixels, Pij. And last time we already said, well, yeah, if they are arranged in a matrix, in an array of CCD elements, then we have basically 2 indices to address each pixel. So what we have here is a set of lots of things and these things are being addressed by a row index I and a column index j. And we just talked about that typically, if it's an intensity image or a gray value image, then we have color values or intensity or gray values ranging between 0 and 255, right? 256 different values, including 0 gives us 0 to 255. For now, this is something we might immediately forget again. This is not really helpful for what will happen in the next couple of weeks. But once we begin talking about binary images, those are images which are represented such that there's indeed just two intensity values for every pixel, either black or white. Once we start talking about binary images, they are interesting for some applications. Once we talk about binary images, this idea of representing images in terms of sets becomes more appropriate or more valuable. The reason why I am showing you this is just to free your minds. Right? You have to get used to the fact that university education is something that is theory-oriented, and this whole lecture will sort of really demonstrate what that is all about. In theory-oriented education, the goal is to provide you, say, with the bigger picture. And once you know about the bigger picture, everything you encounter is just special cases. And you can recognize something as a special case of something more general. And my job is to sort of lead you to this point, that you are able to look at things as, say, special cases of something more general. And one way of doing this is actually really to see, digital images, as we have talked about them so far, indeed can be understood as a set of pixels, where the elements in that set are being addressed using certain row and column indices, and they may have certain values. Right? This is just an example for as to the fact that sometimes there's more than, no pun intended, we see at first sight. Right? Sometimes it is possible for us to take a step back mentally and look at what we are dealing with in a totally different way, and these different ways of looking at things are sometimes very appropriate. And this is, again, we can immediately forget about this for our intents and purposes right now, but it shows you that if we want to, we can. We can think of the things we are dealing with from a totally different point of view. And a way more applicable, or for the time being more applicable point of view on digital images is indeed to understand them as arrays. This is what we have been discussing, briefly discussing last time already. And today we'll ever so briefly generalize what we discussed last time. We'll namely discuss images as n-way pixel arrays. I already said that the domain of a digital image is discrete, and so therefore it is rather straightforward to represent digital images in memory of your computer or your camera in terms of arrays. And by n-way arrays, I refer to the fact that there's different ways of, or different kinds of arrays. A one-way array would be an element or a data structure, say, where we have a data structure, lots of elementary elements, and there is just one index, I don't know, 0, 1, 2, 3, 4, 5, just one index to refer to one of these elements. Right? Now these structures you may know under the name vector, and indeed you can think of them as a vector. In a two-way array, we have two indices to indicate those elementary elements, building blocks. Right? We have a row index, say 0, 1, and a column index, say 0, 1, 2. Now we have 1, 2, and that refers to this element. Right? This, of course, can be continued further. In a three-way array, we have a row, a column, and say a depth index. Right? And in order to refer to this element, given this collection of elements, we would now have to specify three indices. Right? A row index, a column index, and a depth index. So for instance, 0, 2, 1 would give us that element. Now, two-way arrays you may know under the name matrix, and indeed you may think of them as matrices. And a fancy name for three and higher way arrays is tensor. I cannot plot that anymore, but of course we can continue this game. We can create data structures where we would need 15 indices to index or address an elementary element in this data structure. There's no problem there. In general, that is definitely possible. I cannot really plot that anymore, so I confine this slide to 1, 2, and 3-way arrays, or to vectors, matrices, and tensors. And just to illustrate that this is indeed something that may be useful in the context of our study here, I'm showing you that an intensity image, a gray value image, or sometimes also called black and white, but you see that this is not black and white, that an intensity image can be thought of as a matrix. Right? Is a collection of many, many pixels. Each pixel, in our case, assumes a value between 0 and 255. And in order to address a pixel, we'll have to specify the row index and the column index. And then we already talked about color images, and I said that they can be thought of as a superposition of three color layers, or three layers of intensity images, where the first intensity image somehow represents the red content of the scene, and the second one represents the green content, and the third one represents the blue content. And our brain is able to, given these three elementary colors, create all the colors we see from that. And now you see that three such layers of images, or a stack of three such images, is basically, from an abstract point of view, this. Right? And so therefore, one way, for instance, talking about color images is to talk about tensors. And here's, again, something we talked about last time already, the question as to how to address these elements. Note again that now the tiny gaps between the pixels, which are there physically, if we record such images, these CCD elements, they do not really are in spatial contact with it. There's tiny gaps between them, but for all intents and purposes, for our abstract discussions about digital images, we sort of abstract these gaps away, and we say an image is a matrix of pixels. And again, we can address an element in such a matrix using the row and column index. And to indicate, and we have seen that on the previous slides already, that this pixel is at location row I, column J, we use those two indices I and J as subscripts. Right? Subscripts of P indicates sort of its location in this matrix. And yeah, again, like I is the row index, J is the column index. In memory of your computer, the 0, 0 coordinate is typically located up here. Right? So we'll soon see another representation where it's down here, but you know that from your experience as programmers that if you create arrays that basically in languages such as C or Python for that matter, indices are counted starting at 0, right? And if you have two-way arrays, such say a matrix, you would start counting rows up here. This is row 0, 1, 2, 3, 4, 5. You'd also count the columns up here, column 0, 1, 2, and so on and so forth. So that is something you have to keep in mind, in particular, when in practice you switch between different interpretations or representations of images. All right. And very interestingly, we can think of intensity images such as this one. It's a 5x5 image, very simple pattern, either in terms of a two or a one-way array, where the two-way array representation, the matrix representation, is somehow natural. But think of this. What did I do here? Oh yeah. We can vectorize this matrix. And what I have done here is that I've basically taken the first row, which gives me the first 5 elements of this vector. Then I have taken the second row, and that gives me the second 5 elements of this vector, and so on and so forth. And this looks different now, but is indeed actually really, from a very abstract point of view, the same object. Right? And whereas we need 2 indices here to index an element, here we would just need 1 index k. But there is a one-to-one correspondence between these 2 indices I and j and this 1 index k. If we assume that we know the width of the image, in this case is 5 pixels, and let's call this the width of the image, j max. I could have called it width, but whatever. If we know that, then given a pixel with its I and j coordinate, we can immediately compute the corresponding k coordinate in this vector. And this is basically the intensity value in this matrix at location I and j is the intensity in this vector at location I times j max plus j. Let's ever so briefly see if that works. Say we are interested in this pixel here. This is at coordinate 0, 1, 0, 1, 2. So this is at 1, 2. Right? Now, if we verify this equation, we would have to compute 1 times j max. This is 5. So 0, 1, 2, 3, 4, 5. Plus j is 2, 1, 2, and yeah, there we are. It works, right? This bright thing here is this bright thing there. So this works. Can we reverse this equation? Yes. Can we? Yes, we can. Huh? If you don't see that, I sincerely encourage you to do that at home. Think about what it would need to turn this k into I and j. What computation would you have to carry out to go from here to there? Here what we do is we go from the matrix representation to the vector representation, and this is 1 to 1. And the fact that it is 1 to 1 indicates that, well, we can actually reverse it. Think about what you would have to do that. And I'm pointing this out for 2 reasons. The first reason is this is actually how these images are represented in memory. We saw that last time when we had a look into this PPM format. They say that the image is just, you know, a very long sequence of red, green, and blue, red, green, and blue, red, green, and blue coordinates. It's a sequence. It's something like this. Right? This is how images are actually represented in memory. And this is how they are displayed to you. And sometimes you have to do this index gymnastics to go from here to there or vice versa. The second point why I am emphasizing this is, just from looking at this silly example, we realize that we can, if we want to, and later on we will want to, understand an image as a vector. Something that is not immediately apparent if we look at this. This looks very much like a matrix, but we can think of this matrix as a vector. There is a one-to-one relation. Now that we know that, yes, from one point of view, we can think of images as matrices, and that we can address pixels in these matrices using their row and column location indices, we can think of geometric properties or topological properties. It depends on, let's say we can think about stuff like neighborhoods. And in image processing, neighborhoods of a certain pixel play a really crucial role, and we'll see that actually today later on. And there's two common definitions of what it means to be a neighbor of a pixel P. For instance, there's basically two of them. And one of them is the 4 neighborhood. This is illustrated here. And the other is the 8 neighborhood. You can all see the difference between the 4 and 8 neighborhood. What is the difference? Well, here we have just sort of 4 pixels we consider as neighbors, and here we have 8. Why would we distinguish between these two cases?
Well, the 4 neighborhood one, to my opinion, what I see, it only takes into consideration the immediate neighbors of P, whereas the 8 neighborhood takes also into consideration which are the ones that are immediate neighbors to the immediate neighbors of P.
Yeah, I mean, they are still immediate neighbors of P. You're right. These are somehow very immediate. They are also very immediate, but there is a difference. There is a difference. And to understand this difference, let us ever so briefly look into the spatial distances between pixels, picture elements. Say we were given 2 pixels. Let's call them P and Q, and to be well precise, say this one is P and this one would be called Q. I have a Q here, but think of this as P and this one here as Q. When we are given their location in this matrix or on this pixel grid, we can use these 2 indices, the I and j coordinates of pixel P and the I and j coordinates of pixel Q, to compute the Euclidean distance between these 2 pixels, between where they are located. Right? And of course, let's think about these tuples as 2-dimensional vectors, and then we know that the Euclidean distance between 2 such elements is basically the distance or norm of the difference of their locations, of their coordinates, and this is basically IP minus IQ. We have to square that, and 2-dimensional vectors, so to add to that difference squared, JP minus JQ, again square that, take the square root of the resulting sum, and we have the distance between P and Q. Nothing new here. Interesting thing is that for all the pixels in the 4 neighborhood of a certain pixel P, this distance evaluates to 1. Right? So for those 4 pixels, they are at a distance 1 of P. What about these additional 4 pixels in the 8 neighborhood. Yeah?
Square root of 2.
Square root of 2. Let's see. Yes! This is always such a relief. Yes, indeed. They have a different distance. And I don't have to discuss this because, you know, it's square root of 2. And this is actually what distinguishes, in a sense, the 4 neighborhood from the 8 neighborhood. That every pixel in the 4 neighborhood is at a distance of 1, whereas in the 8 neighborhood there are a couple of pixels that are immediate neighbors of the one we are interested in, but they are at a larger distance. Square root of 2 is slightly larger than 1. Is this strange? Nah, not really. I mean, is it or is it not? It's not really strange, but somehow it's also not really necessarily beautiful, right? It's funny that that there are 8 elements surrounding one element we are interested in. 4 of them are at a distance of 1, and 4 of them are at a distance of 2. Is this an artifact of the distance we have used? Can't we consider or define a distance to avoid this strange behavior? The answer is yes, we can or could, and we will discuss that in detail next time. But today we'll basically focus on the question, yeah, why is this? Why are we dealing with structures, mathematical abstractions, matrices, to discuss images or areas of pixels that have this, you know, they're not really so really elegant in the sense that even in the immediate vicinity of a pixel there are things that are farther away than others. Is this because it's impossible to come up with a different representation of images? Is this because it's impossible, we cannot record different kinds of images? Is there a way of recording images such that every pixel is in the neighborhood of a certain pixel is exactly the same distance? Is that impossible? The answer is no. Indeed, if we would really want to, we could avoid this, in quotation marks, strange behaviors. And here is how we could do that. The mathematical study of paving a plane with elementary objects is called, this discipline is called computing tessellations or thinking about tessellation. Here's a couple of examples of tessellations. Some of them you know if you do jigsaw puzzles. This is a Penrose tiling. But look at this one. Now imagine we had a CCD array, a CCD chip that was organized like this. If we had this, then this pixel here would have 6 pixels in its neighborhood. But each of these 6 pixels would be at exactly the same distance. This is somehow, it appears to be, well, I don't know, more principled, probably. Then why don't cameras do this? We could. So if we would want to, we could design CCD chips or digital cameras that would record pictures like this. And indeed, in the science of data visualizations, tilings like this play a very important role. Or for those of you interested in computer games, you know, those maps of computer games are often represented in terms of things like that. So no, I mean, in practice, these things do occur and are very valuable. Why don't we do that when we record digital images? Is there a principal problem there? No. The reason why we don't do this, or humankind doesn't do it, or the producers of digital cameras don't do this, is basically it's not principle but technical. It is rather expensive to create such CCD chips. Can be done and is being done, but not for the consumer market. And once again, if we had this hexagonal tiling, this one here, which has the beautiful property that if this was a pixel, then every pixel in the neighborhood would be exactly the same distance. If we had such a hexagonal tiling, slightly more difficult to represent that in the memory of our computers. And this goes back to what we discussed earlier. If we have these matrices, we can think of them as very long arrays, very long vectors, chunks of memory. You know, starts here at a certain address in memory and ends a couple of megabytes later, but it's, you know, it's one piece of memory, very easy to represent, given the way how memory is organized in our computers today. You have a question?
What is the effect of the longer distance for the human eye?
It is, his question was, is there actually an effect related to this longer distance? Can we indeed see this? Usually no, because the resolution of these images is really so high that artifacts like that are not apparent to the human visual system. However, if we do mathematics with these images, then it becomes important. And I'm really spending so much time on this in one of the early lectures of this series, really just to raise awareness on your parts for these things. Because quite often you find that they are being neglected when it comes to writing programs that do manipulations of images, and then artifacts may become apparent. You had a question.
Yeah. The image representation as we have now, and the theory of image processing,
yep.
is it very dependent on image representation? And for example, if we represent the images in the other way,
yep.
Would we have to neglect half of the theory that we have now, or
no? Yes and no. We have not seen the really important one yet. The really important way of thinking about images is the one we are going to talk about next. But if we are talking about images in terms of matrices, or which is equivalent, and this is really crazy, vectors are equivalent to matrices because there's this one-to-one relation between row and column indices to the just one index in a vector. You can always turn a matrix into a vector. Not necessarily vice versa, that sort of depends on the number of elements in the vector, but every matrix can be turned into a vector. We can then use everything we know about linear algebra to work with these vectors. And of course we could represent these hexagonal images in terms of vectors as well. But then one problem would be that it's not so straightforward to, you know, compute the transition from a two-dimensional tiling sort of to a one-dimensional arrangement. Would we have to throw everything away we know? No, not really, but it would be considerably more difficult. But really, at the core of your question, the answer comes now. Yeah, again, this is really the fact that these things are not considered in practice. And actually somehow they are. For certain applications in, I don't know, the natural sciences, in biology, or there are very, very expensive microscopes who actually have these hexagonal tilings because they just cannot afford to have certain distortions there because they are recording stuff that is of a size very close to the wavelength of light. And if you introduce distortions there, then results you may want to compute from this can be wrong. So these things are used in certain areas, but they are extremely expensive. right? Because it's not being produced for the consumer market, and if you don't produce anything in bulk, it's typically expensive. There's no real fundamental difficulty that it is more difficult though. And now we move on to what will keep us busy for the next couple of weeks to come. Because there is yet another way of thinking of images. And we have talked about sets, we have talked about matrices, which somehow is our way of also referring to vectors and tensors. And now we talk about functions. Again, we said intensity images, and we'll focus on them for the sake of simplicity, are discrete and quantized. For certain discrete row and column coordinates, we have certain discrete intensity values. And because of the fact that certain intensity values, or certain, say, locations in the image are mapped to a certain intensity or gray value or color value later on, we can think of an image as a map or as a function. Right? We can think of an image as a function that takes two input arguments. One is the column index in this case, and the other is the row index. And it maps these two numbers to a third number, which is the intensity or color value at this location. Yeah, and I have switched row and columns here because when we're talking about matrices or arrays, we typically first refer to the row index and then to the column index. But if we talk about functions, we typically first say it's the function of x and y, where x sort of is like, you know, the column direction and y is the row direction. And again, in contrast to this matrix interpretation we have seen earlier, well, I said it, I denotes the columns and J denotes the rows. Now this is, you know, just because this is how they do it in analysis. And whereas the 0, 0 coordinate is located in the upper left for the matrix representation, for this function point of view of images, we assume it to be in the lower left corner. And this is just to confine with the way we learn about functions when we learn about functions in high school or undergrad studies. And why or how or why would I say that that works? Here is an image, and I have enlarged a certain part of this image. Here it's the nose and the eyes of Obelix. And this is a gray value matrix, right? It has rows and columns, and at every location there is a certain intensity value. This is just a visualization of what images are, matrices of intensity values. But if we plot this as a function, where we have sort of the columns and the rows, and then for every index here, say 5 and 5, we would record the corresponding intensity value as, well, a function value at that point, and then plot the whole function, we would see this. Can you see that this makes sense? In the sense that there are areas in this image which we now view as a function that are high up, like, you know, high values, and there are areas in this function that have rather low values. Do these low and high value areas correspond to elements of the image? Yes. Yes, they do, right? And in particular, remember that last time we said something that is very bright is typically represented as a very high or large number, where large is in our case for intensity images like 255. So there is an area in the image that is rather bright, and this corresponds to function values that are much higher than other function values. And Well, just you know, in analogy to that, there are areas that are rather dark that corresponds to rather low values of this function. The reason why I confined this to just a small region in this image is that if I would have plotted the whole image like that, then it's very, very difficult to see any details. But the important take-home message is that if we want to, we can think of these things like that. Okay? And we really want to. We want to think about images as functions. Okay, so here I said that we can think of an image, a digital image, discrete and quantized, as a discrete function. Note that I have used square brackets here instead of parentheses. When usually talking about functions, you know, we have these parentheses. Here we have square brackets. It's a discrete function in the sense that the domain is discrete. This is not all the real numbers, say, but it's certain natural numbers, 0, 1, 2, all the way to something max, and so on and so forth. We may take yet another step back and think of the discrete images or discrete functions in terms of partial functions. And that is to say, we can think of an image as something that maps the plane R2 to intensity values. But instead of a straight arrow, we have this curly arrow here, which I am using to indicate a partial function. And a partial function is a function that is defined over a domain, but not for every element of that domain. It is partial. So it is defined over all the tuples x and y coordinates in the plane, but it is not defined for every possible x and y tuple, but only for some of them. This is what it makes a partial function. And at those points where it is defined, it assumes, like in our case, values between 0 and 255. And this is, again, just to show that if we would want to, we can take a lot of steps back and look at the things we are dealing with from a very abstract point of view. And why would we want to do that? Before I answer that question, I have to point out that from now on, well, we will not really talk about partial functions, but sometimes we do. We're talking about these discrete functions using the square brackets to indicate that I and j are really like discrete elements, not continuous. Sometimes I may write it like this. Instead of I and j, I just use x, where x is a two-dimensional vector, and where we now implicitly understand that this then is a partial function. Why do we do this? Such a complicated matter. Okay, before I answer, here's yet another slide. Sorry about this. Okay, now we have seen, we can think about intensity images. And that is, again, images where there's no color in there, but there's basically gray value images, something very bright, something very dark. Intensity images are functions in the sense we are very used to them. Two-dimensional functions. Certain coordinates are mapped to certain values. Now, color images, so far we have thought of them as consisting of three matrices, being a tensor. We can think of them as what is called a vector field, which is to say a color image is a function that maps spatial coordinates to vectors. Note that there is a power of 3 here now. This is a function that takes a 2-dimensional coordinate, some coordinate here, and maps it to a 3-dimensional vector. Right. And this 3-dimensional vector contains 3 numbers, one for the red value at that coordinate, one for the green value at that coordinate, and one for the blue value. So this idea of understanding images as functions carries through to color images, and these kind of functions are typically referred to as vector fields, where we have something that assigns every coordinate, every location in this, or some of the locations if it's partial, some of the locations in this space are being assigned a vector. Okay, now finally, I'm sorry, why do we do this? Why would I torture you? The reason for taking so many steps back when we are looking at the objects we are interested in here, digital images, is that once we understand them to be a manifestation of something we have been dealing with ever since high school, functions, we can use everything we know ever since high school to work with functions. And that is to say, stuff we know about what we can do with functions, we can now apply to images. And the idea of understanding images as functions allows us to do a lot of computation with images. And this is the basis of image processing. And to appreciate that, let us look at an example to wrap up our discussion for today. A question? No. And here is the example. And again, to fully appreciate this example, we have to step lots of steps back and go back to high school and recall what we know about deriving functions, computing the derivative of a continuous one-dimensional function. So the object we are dealing with in our discussion right now is a function depending on one variable. Just one variable, not on two, we'll get to that. And we want to understand the idea of deriving such a function, of computing the derivative. And you recall that there is two things that are defined in this context, namely the derivative from above and the derivative from below. And just recall that the derivative from above, I'll write it as f prime plus at x, is given as the limiting process where we consider the value of the function f at x plus some epsilon, which will become very small, minus the value of the function at x. And this difference is being divided by epsilon. And if this epsilon is becoming ever smaller, moves towards 0, the limit of this expression is called the derivative from above. And vice versa, the derivative from below, f prime minus, is basically the difference between the value of the function f at x minus the value of f at x minus this epsilon, divided by this epsilon. Again, this will be made very, very small. The limit of this expression is called the derivative from below. And once we have at least accepted that these two things do exist, then we can define what it means for a function f to be differentiable at a certain point x. And this is basically to say that the derivative from above and the derivative from below coincide. That the derivative from above is exactly the same as the derivative from below. If that is the case, we shall call it f prime or d dx of f of x. And here is an example. I have plotted for you the function x squared. So the function we are interested in, f of x, is x squared. We are interested in the derivative of this function at x equals 2. And I have plotted this limiting process. We start somewhere with, say, epsilon equals 2. And if I plot this function here, where I substitute 2 for epsilon, this is a linear function. If I plot it, it looks like this, right? If instead of 2, I would use 1 for epsilon, we get this function. For 0.5, we get this function. And if it becomes really small in the limit, we get this function here as the derivative of f of x equals x squared from above. And here I have repeated this for the derivative from below. See that it looks different than the derivative from above. But for decreasing epsilons, it does not look so different anymore. And indeed, in the limit, it's exactly the same. Which is, of course, no surprise, because we know that x squared can be differentiated. X squared is differentiable. Which is another way of saying that at every point of x squared, the derivative from below and above do coincide. Does not have to be the case. There are many, many functions f of x that are not necessarily differentiable in any point, because sometimes the derivative from above and below are not identical. So x may not necessarily be differentiable. But at least for continuous functions, we have a grasp as to what it means to be differentiable. Now, images are discrete functions or partial continuous functions, as you like. How then would we try to define the notion of differentiability of a discrete function? Well, let's, just proceed as we just did. So we now consider a discrete one-dimensional function. And this is a function, note the square brackets, not the parentheses. It's a discrete function that depends on one argument only. Well, we can, of course, define this idea of derivative from above, just as we did with the continuous functions. So we could consider the derivative from above of this function. I'll write it down as delta plus. And this is a very unfortunate choice. The name delta you'll see later on, but let's ignore it. Delta plus, say, the derivative of this discrete function from above. Well, if we sort of repeat what we just did, we would say, okay, this is f at I plus 1. Without loss of generality, we assume that these coordinates I are 1 apart. F at I plus 1 minus f at I divided by this epsilon, which is I plus 1 minus I plus 1 minus I, which is 1. So basically the derivative from above is f at I plus 1 minus f of I. We can do that, and we can repeat that for the derivative from below, and we will run into a problem. Because as the function now is a discrete function, we cannot consider these limiting processes. These epsilon goes towards 0. It's not possible here because, well, these things are discrete. There is no continuum between them that can become arbitrarily small. There is no limiting process here. This is because if we define it like that, the denominator will always be 1. I, left it out here because dividing something by 1 is not so interesting. And because of that, derivatives from above and below will in generally be different. Here is an example. So what I am plotting you here is a discrete function, and I am indicating the fact that this function is discrete. There's like no continuous plot here, but there are these dots with the candlesticks. This is meant to indicate that this function is discrete, And it is indeed the function I square, so it's sort of the discrete equivalent of the continuous function we have looked at earlier. And here we see the derivative from above of I square at 2 is this line. It's again a linear function. And here we see the derivative from below of I square at 2. And they are different. Right. And we just said for continuous functions, the notion of it is differentiable at a certain point is defined as, and this is really how differentiability is defined. The derivative from above and below are the same. Now we see that for discrete functions, we'll have a very hard time to guarantee that those two are the same. When would they be the same? Linear, exactly. So if this was not I square, but say, I don't know, 2 times I, then we would be good, then no problem. But in general, we cannot guarantee that they are the same. And this is sad because the things we are dealing with are these discrete functions. And I just said if we consider images as functions, we can use everything we have learned in high school and apply it to images, and now it appears that we cannot. Well, we still can, but we have to compromise. And one compromise, for instance, is that we don't throw away the idea of differentiability, but we adapt it to the things we're dealing with. The things we're dealing with are discrete functions, and one way of adapting the idea of differentiability to discrete functions is, for instance, this definition of the derivative of the function f at I. We define it from now on using, this is my definition, and you will find different ways of defining any literature. This is sad, literature can't really agree on what it means, but this is one possible way. We will include information from above and below and define the derivative of a discrete function f at I as f at I plus 1 minus f at I minus 1. And for our example, it then looks like this. So it's again the function I square, and now this is the function that would be produced if we were to compute the compromise or our definition of discrete derivative. And you see it's not as steep as the derivative from above, and it's not so steep as the derivative from below. So it's indeed a compromise. Right? So this is how we agree to adapt differentiation to discrete functions. We can then move on to the stuff we are dealing with. If we are talking about functions with more than one variable, say a function f of x and y, the derivative can be generalized in terms of the gradient. If we consider multivariate continuous functions, and by multivariate I mean functions that depend on several arguments or parameters, can generalize this idea of differentiability. First of all, we can consider partial derivatives of these functions. That is, we can consider the derivative of this function, say, just with respect to this variable. And this is being written using these curly d's here. So this is the derivative of x only with respect to parameter x1. And this would be the derivative of x only with respect to parameter xn. Now, if we were to compute all these partial derivatives of a given function and collect them in a vector, then this vector is called the gradient of this function. And given that we have agreed that we can adapt the idea of differentiability from continuous functions to discrete functions, we can then of course adapt the idea of computing the gradient. This thing here is, for those of you who it is called the nabla operator. So if I have this triangle standing on its pointy head, this is called nabla of f, or gradient of f. We can adapt the gradient for continuous functions to discrete functions. And since we are interested in functions defined over two variables, I and j, I'll focus on this immediate example here, is basically the derivative, or the gradient of this discrete function is a vector, where in the first component we have the derivative of the discrete function with respect to the x-coordinate, which is I in our case, and the second component would be the derivative, partial derivative of the function with respect to the y-coordinate, j, right? So given what we said is the derivative of a discrete function, we just plug it in here. So this here, derivative with respect to I, is g of I plus 1, comma j, minus g of I minus 1, comma j. Straightforward application of what we just defined here. Now, this was a function depending on just one variable. Now we're dealing with a function depending on two variables, but we can use our definition as the partial derivative for, say, the I coordinate. And if we do that for j, we have j of I, comma, g of I, comma j plus 1 minus g of I, comma j minus 1. So no problem, yeah?
If we use that equation, so we losing the real information of g I and j.
Yeah, but what can we do? You're right. So she was worried if we are losing information, like because of the plus 1 and minus 1 here, right? Yes, we do, but it's a compromise, right? Let's again. Yeah. So we are dealing with this as opposed to either this or this. And I said this is how I will define it, and it's not, you know, my crazy fantasy here. Of course, other people do it like this as well. But there are many different possibilities as to how we could adapt this idea of differentiation from the continuous case to the discrete case. This is just one way. This will lose, in a sense, information about the value at I. Yeah, that's true. But, yeah.
Well, we don't need to divide these two.
Yeah, it's again a compromise. Like, okay, so she was asking, why don't we divide that by 2? Bah! Yeah, why don't we? We don't. See, this is embarrassing now, because I said everything is well understood and there's no question I couldn't answer. This is indeed, there's a definition. There's a definition. We could divide it by 2, but we don't. We don't.
Well, it's a scalar factor, right? So.
Yeah, it's just a scalar factor. I mean, like, it doesn't make much of a difference. Like, it's not. Right. I can see that. I can see why you are concerned, because here we sort of divide by 1, and the sort of difference is 1, and we should probably divide by 2, because here the difference is 2, but we don't. Should we?
But for the next, the graphic, the picture,
Yeah.
the scale seems we used to divide. And yeah, for this.
Maybe I have done it. I really don't know. I don't know. I probably should check the code I used to compute this here. It's a very valid point. Very valid point. I might have actually divided it by 2. I don't know. I'll come back to this next time. It does not really matter, because it's just, you know, it's just a factor. It's just a factor, and we can sort of always pull it out. But now that we're discussing this is again, there are many and let's go back to the gradient. This is just one way as to how we can think of the gradient of a discrete function. And if you start reading books or whatever on image processing, you will find numerous different equations here. So I say the gradient is defined as this. This is what I'm saying. But if you read other books, you'll find other definitions there. And they all have their same name: Roberts gradient, Sobel gradient, Kenny gradient. There's so many different gradients for digital functions. Why? Because it's not really clear how to derive a discrete function. And so we somehow have to carry through this idea of derivative from above and below to the case of discrete functions. And there are many different ways as to how we can do that. And this is just one. I'll check if in this picture I indeed divided it by 2. It looks like as I did it. Yeah, you're right. So maybe I'll come back to that later. But now, this is how, for the time being, we adapt this from the continuous case to the discrete case. And here's one thing I wanted to point out, because this will haunt us, not so much with respect to the gradient, but with what is to come. I wanted to point out that this thing here, nabla, or the gradient, is an operator. And an operator is a function that takes as an input a function and produces another function. So it is a function that operates on functions. And we have to, it takes a function and produces another function. And this is different than the functions we are, I guess, familiar with, which take numbers and produce another number or tuples of numbers. So the functions we are hopefully very familiar with operate on tuples of numbers and produce other tuples of numbers. Operators, such as this one, take a function and produce a function. So operators are, in a sense, generalizations of the functions we are used to. Okay, and just given the way we have defined it, it's of course immediately obvious that it's another discrete, and in our case vector-valued function. That is to say, it's a discrete vector field. We briefly talked about vector fields earlier. The question is, how could we visualize the effect of applying the gradient operator to an image function? Quite often, what we do is, when we have computed the gradient of an image, is we plot the norm of this. Again, gradient of G is a vector, 2-dimensional in our case, because G has an x and a y direction. And so if we compute the Euclidean norm, it is basically, again, the inner product of this vector with itself, and then we have to take the square root, and we can also write it like this, blah, 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 blah. Let's have a look at an example. So here we go. This is the image, and what I have computed here is just the derivative of the image with respect to the x-coordinate. And what I have computed here is the derivative of the image with respect to the y-coordinate. And I don't know if you can see the difference. Maybe if you look at those slides at home, you will see that these edges here are different than there. Here basically the edges sort of say very pronounced if there's a strong difference between something along the x direction. Here the edges are very pronounced if there's a strong difference stuff in the y direction. And what I have plotted here is what we discussed here. So after having computed the gradient, we can immediately visualize sort of the y derivative and the x derivative of the image. And here is a visualization of the magnitude of the gradient. That is, again, for every location in the image, We have computed this gradient, and then we compute the norm, the Euclidean norm of the resulting vector. And also, if this expression exceeds a value of 255, I round it off to 255. Right. Can this expression fall below 0? The norm here? No, cannot, right? So we don't have to worry about that's like, you know, it cannot. It's a norm. So it has to be larger or equal than 0. So we don't have to worry if what happens with pixels that get a value of -5. That it does not happen. But it may happen that this here has a value of 380, whatever. I don't know. If that happens, I just brutally, for the visualization here, I set it to 255. Right. So here we see a visualization of the magnitude of the gradient of this function. Looks like an image, but we treat it like a function. And here, and this has to be taken with a grain of salt, is a visualization of the gradient in terms of a vector field. So you will not be able to, but there's lots of tiny arrows here. There's like these arrows where, because at every location in this domain here, we have computed the gradient, and the gradient is a vector, so every point is being mapped to a vector. This is a vector field, but I can only plot it at every 10th location actually, because otherwise this would be just black because of all the tiny arrows. So take it with a grain of salt. You can try to create such a plot at home. You will see if you do it at every coordinate, you see nothing. So what I did here is I basically just plotted the gradient at every 10 coordinates. So careful is not really the vector field of the vector, but it's just sort of a representation of the vector field, a subsample of the vector field. And at home, you can see that these indeed are all very tiny arrows. What is this good for?
Finding edges.
Yes. What did you want to say?
She just answered.
Yeah, so she said for finding edges. Yes, it detects edges. Great. Pardon?
Features detection.
Yeah, that was my next question. Why would we want to detect edges? You already said it. There are numerous reasons for us to try to detect edges in an image. And we will study them in incredible detail much later on. Most of that in the next semester. But we have now, like with our really elementary discussion today, we have seen images are functions. We can do stuff with functions that we are used to do with functions. Right? We can derive them. And if we, for instance, derive these kind of images we have looked at as examples, just from looking at these examples, we see, it finds edges. And this is something we might, really make use of a lot later on. For now, we will consider a more prosaic application of all of this. So we have realized that by computing gradients, we can find edges. And now we will use that to make or to create an artistic image effect. And the ones we will create is, or the idea we are after, is to transform an image in a way such that it looks like a copper engraving or etching. And what I am going to show you is that very similar to what we just did when we computed the gradient of this image, we will compute something quite similar and use what we compute, do something more with it to create a new image. So here's what we do. We will, given an image g, which we understand as a function from now on, right? Given a function g, we compute this. What do we do here? What is it? G of I plus 1, comma j plus 1 minus g of I minus 1, comma j minus 1. What does that do?
I guess will be it finds different gradients along the diagonal.
Yeah, almost there. It computes the differentiation along the diagonal, right? Because for a gradient we would have a vector here, but this is just sort of it's just, you know, one dimension. But you're right. This is, look at it. This is the differentiation we talked about earlier, but not along the x or y direction, but along the diagonal direction. All right? So we compute this. We get a value. To this value we'll add the number 128. And we do this for all the coordinates of the function g, and the result will be called g tilde. And here's how that looks like. This is g, this is g tilde, this is g, this is g tilde. So it has indeed created something that is similar or that resembles a copper engraving, right? Like these old kinds of, like when in printing people had to plates of copper using chisel and then, you know, create stuff that looks like this. And here you have it. Do you have any questions about this? I'm just curious because usually I get lots of questions when people look at this. Last time I taught this course, people were very unhappy with this bright edge here because there is no bright edge here. Is indeed. Pardon?
It's engraving.
Yeah, the thing is, I would never have thought that this is actually something that would raise concern, but I was glad about the fact that it did raise concern, because it shows us that if we do something with images, for instance, this effect here, sometimes something becomes visible that is not necessarily visible to our eyes in the original image. So in that sense, we already can understand the fact that it may be interesting to do certain computations with images in order to pronounce certain content in these images. And indeed, there is an edge between the arm of the baby and the background, but it's very blurry or hardly visible because it's very dark. But if we apply this operation to the image, then all of a sudden it becomes very pronounced. Right? So to me, there is no reason to worry. In fact, we already also see that something appears up here which we really don't see here, but it would not appear if it wasn't there. So sometimes indeed these things of these operations we apply to images, these operators we apply to these functions, provide us with new insight which is not as obvious from looking at the original image. And this, to wrap it up, is the first example, first very simple example of artistic image effects. Right? For people who like copper engravings, I don't know, they may like this, I don't know. Okay, to summarize what we have learned today. We have looked at different mathematically abstract ways of looking at images. And the most important thing to note is we have seen that we can understand images as n-way arrays, vectors, matrices, tensors. And in particular, if you're given a tensor, we can understand it as a very large matrix, which we can understand as a vector. So images are vectors. We'll come back to that later. Then we saw, and this will keep us busy for the next couple of lectures, that images are certain functions, discrete functions or partial functions. We can think of them as functions. Once we know that images are functions, we can do whatever we want to with these functions, what we are sort of used to do with functions. We can apply operators to functions. One of the operators we saw today was the gradient operator. We can apply these kind of things to images. And we sort of discussed one way of adapting what we know about continuous functions to the realm of discrete functions, in particular with respect to derivatives and gradients. And we already had a discussion as to the merits or reasons for why to do it like this. And remember, there is very many different ways of how we could do this. In this lecture, we do it like that. Okay? So don't be alarmed if you read something else somewhere else. That is just to be expected. For those of you who want to dig deeper, try to work with what we just learned. Think about this. First exercise refers to the notion of the divergence of a continuous multivariate function. And here is why it's very unhappy that I used the delta earlier on, because the divergence operator is just something like the gradient operator. It's an operator that operates on a function. It's also called the Laplace operator. Is defined like this. This is the definition of the divergence of a multivariate continuous function. Now, this is the definition of a multivariate continuous function. Can you adapt that, given what we discussed today, to discrete functions? Give it a try. Come up with a definition of the divergence for discrete, say, two-dimensional functions. And then, for the sake of simplicity, consider one-dimensional functions, say g of I, and think about what these two operators do. Right? This is am applied to g of I, and this is wm applied to g of I, and this is what they do mathematically. So what do they do in your own words? What do these two operators do? If you want to, think about this at home, and this is all I have for today. Are there any questions? Well, if not, then we see each other again next Monday, because this Thursday I have to go to Berlin, right? See you then.